A microscopic gap is all it takes. Under immense pressure, an industrial pipe joint can turn a tiny seating imperfection into a catastrophic vapor leak. To prevent these high-pressure blowouts, industrial engineers rely on the ASME PCC-1 guidelines. This standard provides the exact mathematical baselines required to guarantee a safe, reliable seal. Today, we are going to walk through how to apply this standard in the field. We will cover how to measure pre-disassembly gaps, map the surface flatness, and calculate exact defect tolerances. Before taking a single measurement, we have to define the hardware. The PCC-1 standard categorizes all rules based on whether you are installing a hard-face gasket, which is unforgiving, or a soft-face gasket, which has more compression and can tolerate slightly more variation. Preventing a high-pressure breach relies on measuring fractions of a millimeter against these rigid, unyielding standards. The inspection protocol actually starts before you open the joint. Your first step is to check the gap between the outer edges of the raised flange faces. You need to measure this distance all the way around the circumference. To pass, the gap must be at least 1.5 millimeters, or 0.062 inches, at every single point. If the gap falls below that threshold, the metal flange faces risk touching each other when bolted together. When the faces touch instead of fully compressing the gasket, joint leakage is practically guaranteed. Once you have verified the gap and safely disassembled the joint, clean the seating surface completely. You are looking for any physical damage, dents, or scratches across the bare metal. If your visual sweep reveals actual cracking inside the gasket groove, stop the standard inspection immediately. Cracks require a specialized repair protocol, and you will need to refer directly to ASME PCC-2, Article 305 for your next steps. By checking the external gap before opening the hardware and scanning for critical fractures immediately after, you can predict and prevent mechanical failure before you even begin the micro-measurements. With the surface clean and intact, we need to ensure the flange is actually flat. We start by measuring the circumferential flatness of the gasket seating surface. Looking at figure D21 from the ASME standard, you can see the precise alignment method. You must set your measurement tool and establish the datum at 4 distinct points around the full circumference of the seating area. Moving to figure D22, we measure radial variation. You take measurements along radial lines across the gasket seating surface, repeating this every 200 millimeters or less until the entire face is mapped. You then cross-reference these high and low measurements with the tolerances listed in Table D21. Because soft gaskets compress more easily, they allow for slightly more topographical variance than hard gaskets. A surface might look perfectly smooth to the naked eye, but true flatness is a mathematically mapped topographical reality. A defect's danger depends on 2 variables, the total face width, W, and the radial dimension of the defect, RD. Before checking limits, calculate depth correctly. Measure starting from a strict baseline across the surface serration peaks, straight down to the defect's bottom. Now we compare the sizes. For small defects where the radial width is less than 1/4 of the total face width, hard-faced gaskets allow a depth of up to 0.76 millimeters. Soft-faced gaskets allow up to 1.27 millimeters. If the defect takes up between 1/4 and 1/2 of the face width, the depth tolerances tighten. Hard-faced gaskets are restricted to 0.25 millimeters deep, and soft-faced drop to 0.76 millimeters. When a defect spans between 1/2 and 3/4 of the face width, the rules change drastically. This size is strictly not allowed for hard-faced gaskets. For soft-faced gaskets, the maximum allowed depth shrinks to just 0.13 millimeters. Then there is the absolute failure rule. If any defect's radial dimension exceeds 3/4 of the flange face width, it is an automatic failure. Neither hard-faced nor soft-faced gaskets are permitted. There is one critical exception to remember. Ring-type joint, or RTJ gaskets, must always be evaluated under the strict hard-faced tolerance rules. An isolated defect depth measurement tells you very little on its own. Its potential to cause a catastrophic leak is dictated entirely by its proportional footprint across the flange face. By calculating the precise radial dimension and depth against these ASME thresholds, you now have a definitive pass or fail condition for your hardware. However, if your measurements exceed these limits or fall right on the borderline, the standards require professional engineering judgment. An expert must assess the joint's leakage history, hardware flexibility, and specific operating risks before the system can return to service. We started by verifying external gaps to prevent flange collisions, mapped the topographical flatness to guarantee a true seal, and calculated exact defect geometry against strict tolerances. If this breakdown helped clarify your inspection protocol and saved your hardware from a leak, please like the video and subscribe to the channel for more in-depth industrial maintenance tutorials. Meticulous human execution transforms these technical standards into a functional, leak-proof reality.